Hello there, and welcome to the Midnight Physics channel. I'm so glad you found your way here tonight. Perhaps you have had a long day, or maybe you are simply someone who prefers drifting off to sleep with cosmic wonders floating through your mind, rather than counting sheep. Either way, this journey is made just for you. Tonight, you have nothing to do but rest. Let your shoulders drop, let your breathing slow, and let your body grow light as if gravity itself has loosened its hold. Because tonight we are not just reading about space, we are floating through it. From the vast observable universe to the smallest particles dancing between stars, from ancient light that has traveled billions of years to reach your eyes, to mysteries we have only begun to understand. You will hear of exploding stars and wandering planets, of time itself bending near black holes and galaxies, colliding in slow cosmic ballets. Some of what you hear tonight may surprise you, or at the very least spark some quiet curiosity as you drift toward sleep. And just before we begin, if these gentle, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let us begin. The universe is approximately 13.8 billion years old. Scientists determine this age by studying the cosmic microwave background radiation, the afterglow of the Big Bang that still fills all of space. This measurement comes from data gathered by the Wilkinson Microwave Anisotropy Probe and the Planck satellite, which mapped tiny temperature variations in this ancient light. The precision of this measurement is remarkable, with an uncertainty of only about 59 million years. In cosmic terms, that is like knowing someone's age to within a few hours across an entire lifetime. This ancient universe has been expanding, changing and evolving for longer than we can truly comprehend, and yet we live within it, tiny witnesses to its grandeur. The observable universe is 93 billion light-years across. This seems impossible at first because if the universe is only 13.8 billion years old, how can we see things that are farther away than light could have traveled in that time? The answer lies in expansion. Space itself has been stretching all this time, carrying distant galaxies away from us faster and faster. So while light has been traveling for 13.8 billion years, the objects that emitted it have been moving away the entire time. The edge of what we can see, the observable universe, is now approximately 46 billion light-years away in every direction. Beyond that horizon lies more universe, perhaps infinitely more, but we will never be able to see it. The light simply has not had time to reach us yet, and may never will. The universe is expanding, and that expansion is accelerating. In 1998, two teams of astronomers made a shocking discovery while studying distant supernova explosions. They expected to find that the expansion of the universe was slowing down due to gravity, but instead, they found the opposite. The universe is expanding faster now than it was billions of years ago. This discovery was so important that it led to three astronomers, Saul Perlmutter, Adam Rees, and Brian Schmidt, being awarded the Nobel Prize in Physics in 2011. This acceleration is driven by something we call dark energy, a mysterious property of space itself that seems to push everything apart. We do not know what dark energy is, but it makes up about 68% of the total energy content of the universe. Most of the universe is invisible to us. Only about 5% of the universe is made of ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us. Another 27% is dark matter, which we cannot see but can detect through its gravitational effects. The remaining 68% is dark energy. Together, dark matter and dark energy make up 95% of everything, and we do not truly understand what either of them is. It is humbling to realize that nearly everything in the universe remains a mystery. The visible stars and galaxies we photograph and study are merely a tiny fraction of what exists, like seeing only the foam on top of a vast ocean. The cosmic microwave background fills all of space. This faint glow is the oldest light in the universe, released about 380,000 years after the Big Bang. Before this moment, the universe was too hot for stable atoms to form. It was a glowing plasma of particles and radiation. Then the universe cooled enough for electrons to combine with protons, forming the first hydrogen atoms. Light could finally travel freely through space. That ancient light has been traveling ever since, stretched by the expansion of the universe into microwave wavelengths. When we map this radiation, we see tiny temperature fluctuations that became the seeds of all cosmic structure, the galaxies and galaxy clusters we see today. Every direction we look in space, we see this ancient glow, a cosmic baby picture of the universe itself. Our sun is an average star, unremarkable in the grand scheme of things. It is classified as a yellow dwarf, a main sequence star that burns hydrogen in its core. The sun is about 4.6 billion years old, approximately halfway through its expected 10 billion year lifespan. When it runs out of hydrogen fuel, it will swell into a red giant, possibly engulfing the inner planets, including Earth. Eventually, it will shed its outer layers and collapse into a white dwarf, a dense ember slowly cooling over trillions of years. But all of that lies far in the future. For now, the sun shines steadily, providing the warmth and light that makes life on Earth possible. It is neither the hottest, brightest, nor most massive star in our galaxy, but it is ours, and we orbit it faithfully. Light takes 8 minutes and 20 seconds to travel from the sun to Earth. This means that when you look at the sun, you are seeing it as it was 8 minutes ago. If the sun suddenly vanished, we would not know for 8 minutes. This time delay exists because light, though incredibly fast, still has a speed limit, about 300,000 kilometers per second. Nothing in the universe travels faster. The light leaving the sun has journeyed through 93 million miles of empty space before it reaches your eyes. Each photon of sunlight hitting your skin began its journey deep in the sun's core, where nuclear fusion creates energy. That photon bounced around inside the sun for thousands or even millions of years before finally escaping into space and racing toward Earth. The sun is just one of at least 250 billion stars in the Milky Way. Some estimates put the number even higher, perhaps 500 billion. Our galaxy is vast beyond imagination, and each of those stars is a sun, many with their own planetary systems. And the Milky Way is just one galaxy among trillions in the observable universe. The total number of stars in the universe is estimated to be around 200 billion trillion, though the true number is unknowable. When you look up at the night sky, you see only a few thousand stars with the naked eye, barely a whisper of the cosmic chorus. Stars are born in clouds of gas and dust. Deep within the coldest, darkest regions of space lie vast molecular clouds, and nurseries where stars begin their lives. These clouds can span hundreds of light years across and contain enough material to form thousands or even millions of stars. Gravity slowly pulls the gas inward, and as it collapses, it heats up. At the center of a collapsing region, temperatures and pressures rise until nuclear fusion ignites. A star is born. This process takes millions of years, but from a cosmic perspective, It happens in the blink of an eye. Once fusion begins, the new star blows away the surrounding cocoon of dust and gas, revealing itself to the universe. The closest star to our Sun is Proxima Centauri, about 4.2 light-years away. This tiny red dwarf orbits as part of the Alpha Centauri triple star system. If you could travel at the speed of light, it would take you 4.2 years to reach it. With current technology, it would take thousands of years. Despite being our closest stellar neighbor, Proxima Centauri is too faint to see with the naked eye. It burns slowly and steadily and will likely outlive our Sun by trillions of years. Recently, astronomers discovered at least one planet orbiting Proxima Centauri, making it the nearest known exoplanet system to Earth. Supernova explosions can briefly outshine entire galaxies. When a massive star reaches the end of its life and runs out of fuel, its core collapses in a fraction of a second. The outer layers rebound in a catastrophic explosion that can release as much energy in a few weeks as the Sun will emit over its entire 10 billion year lifetime. These supernovae scatter heavy elements like iron, gold, and uranium into space, enriching the interstellar medium. New stars and planets forming from this material will contain these elements. Every atom in your body heavier than hydrogen or helium was forged in the heart of a dying star. We are all made of stardust, remnants of ancient stellar explosions. Neutron stars are the densest objects in the universe besides black holes. When a massive star explodes as a supernova, its core can collapse into a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. Neutron stars are typically only about 20 kilometers across, roughly the size of a city, yet they contain more mass than our Sun. The gravity is so intense that the surface is perfectly smooth. Mountains taller than a fraction of a millimeter would collapse under their own weight. Some neutron stars spin hundreds of times per second, creating pulsars that sweep beams of radiation across space, like cosmic lighthouses. White dwarfs are the final state for most stars, including our Sun. When a star like the Sun exhausts its nuclear fuel, it sheds its outer layers, leaving behind a hot, dense core called a white dwarf. These stellar remnants are about the size of Earth, but contain roughly half the mass of the Sun. They shine not through fusion, but by radiating away their stored heat. Over billions of years, white dwarfs slowly cool and fade, eventually becoming cold. Dark cinders called black dwarfs. However, the universe is not old enough for any black dwarfs to exist yet. Every white dwarf we see is still glowing faintly with the memory of its former brilliance. Variable stars pulse in brightness over regular intervals. Some stars are not constant in their light output. They expand and contract like slow, luminous heartbeats. Certain types of variable stars, such as Cepheid variables, have a well-known relationship between their pulsation period and their true brightness. By measuring how long a Cepheid takes to brighten and dim, astronomers can determine its actual luminosity. Comparing that to how bright it appears allows them to calculate its distance. These stars serve as cosmic yardsticks, helping us map the structure and scale of the universe. They were crucial in Edwin Hubble's discovery that the universe is expanding. Some stars orbit each other in binary or multiple systems. More than half of all stars in our galaxy are not solitary like the Sun. They have companion stars, locked in gravitational embrace, orbiting their common center of mass. Some binary stars are so close they exchange material, while others orbit at vast distances, barely influencing each other. When these systems are aligned just right, one star can pass in front of the other from our perspective, creating an eclipse. By studying these eclipses, astronomers can determine the sizes, masses, and even surface temperatures of stars with remarkable precision. The Milky Way is a barred spiral galaxy. Our home galaxy contains over 100 billion stars, arranged in a flat disk with spiral arms curling outward. At the center lies a bar-shaped structure of densely packed stars, and at the very heart sits a supermassive black hole called Sagittarius A star, more than 4 million times the mass of the Sun. The Milky Way is about 100,000 light-years across, and we are located in a minor spiral arm called the Orion Spur, about 26,000 light-years from the galactic center. From our vantage point deep within the disk, we see the galaxy as a hazy band of light stretching across the night sky. It takes our solar system about 225 to 250 million years to orbit the galactic center. This vast orbit is called a galactic year. The Sun moves through space at about 828,000 kilometers per hour, yet the galaxy is so immense that each circuit takes hundreds of millions of years. Since the solar system formed about 4.6 billion years ago, we have completed only about 20 orbits around the Milky Way. The last time we were in this part of the galaxy, dinosaurs had not yet appeared on Earth. By the next time we return to this spot, who knows what will have become of our planet and species? The Milky Way is on a collision course with the Andromeda Galaxy. Andromeda, our nearest large galactic neighbor, lies about 2.5 million light-years away. Despite this vast distance, the two galaxies are slowly falling toward each other under mutual gravitational attraction. In approximately 4.5 billion years, they will collide and merge. Do not worry, though. The distances between individual stars are so vast that actual collisions are exceedingly rare. Instead, the two galaxies will pass through each other, their shapes warping and twisting, before eventually settling into a single, larger elliptical galaxy. By then, our Sun will be nearing the end of its life, and Earth may already be uninhabitable. The Milky Way has eaten dozens of smaller galaxies over billions of years. Our galaxy has not grown alone. It has consumed smaller dwarf galaxies that wandered too close, slowly tearing them apart and incorporating their stars into the Milky Way's halo and disk. Astronomers have identified streams of stars wrapping around the galaxy, remnants of these ancient mergers. One especially large event, the Gaia-Enceladus merger, occurred billions of years ago and added many stars to the Milky Way. The galaxy we see today is a composite, stitched together from the remains of countless smaller systems. There are at least 2 trillion galaxies in the observable universe. This estimate comes from deep space surveys conducted by telescopes like Hubble and the James Webb Space Telescope. Each of those galaxies contains hundreds of billions of stars. The sheer number is almost incomprehensible. And remember, this is just the observable universe, the part we can see. Beyond our cosmic horizon, there may be infinitely more. Each galaxy is a city of stars, many with planets, and perhaps some with life looking up at their own night skies, wondering if they are alone. Galaxies come in different shapes and sizes. Some, like the Milky Way and Andromeda, are majestic spirals with curving arms. Others are elliptical, smooth and featureless, shaped like cosmic footballs or spheres. Still others are irregular, chaotic collections of stars with no clear structure. The shapes often tell stories of galactic history. Elliptical galaxies usually form from mergers between spirals. Irregular galaxies may have been disturbed by gravitational encounters. And then there are strange, rare types like ring galaxies, formed when one galaxy punches through the disk of another, creating ripples of star formation spreading outward like waves on a pond. Dark matter holds galaxies together. By all logic, the outer edges of galaxies should fly apart. The visible stars and gas do not have enough mass to hold themselves together with gravity at the speeds they are rotating. Yet galaxies remain intact. The answer is dark matter, an invisible substance that outweighs all visible matter in a galaxy many times over. We do not know what dark matter is made of. It does not emit, absorb, or reflect light. We detect it only through its gravitational effects. It forms vast halos around galaxies, invisible scaffolding that keeps everything in place. Galaxy clusters can contain thousands of galaxies bound together by gravity. These are the largest gravitationally bound structures in the universe. The Milky Way belongs to a small group called the local group, containing about 50 galaxies. But some clusters are far larger, containing thousands of galaxies swarming like bees in a hive. The space between galaxies in a cluster is filled with hot, X-ray emitting gas, so hot it does not collapse into stars. These clusters are connected by even larger structures called superclusters. And beyond that lies the cosmic web, a vast network of filaments and voids spanning billions of light years. Quasars are the brightest objects in the universe. These incredibly luminous objects are powered by supermassive black holes in the centers of distant galaxies. As matter spirals into the black hole, it heats up and emits tremendous amounts of light, sometimes outshining the entire galaxy surrounding it. Quasars are so bright they can be seen from billions of light years away. Most quasars existed in the early universe when galaxies were younger and their central black holes were actively feeding. Today, quasars are rare. The supermassive black holes in most galaxies, including our own, have calmed down, resting quietly at galactic centers. The James Webb Space Telescope has revealed galaxies as they appeared shortly after the Big Bang. Launched in December 2021, Webb has infrared eyes that can see through cosmic dust and peer back to some of the earliest moments of cosmic history. It has found galaxies that formed when the universe was only a few 100 million years old, barely 1% of its current age. These ancient galaxies appear surprisingly mature, with structures and masses that challenge our understanding of how quickly galaxies can form. Each discovery raises new questions and rewrites textbooks, reminding us how much we still have to learn. Our solar system formed about 4.6 billion years ago from a collapsing cloud of gas and dust. A nearby supernova explosion may have triggered the collapse, sending shockwaves through the cloud. As it collapsed, the material began to spin, flattening into a disk. At the center, gravity pulled more and more material together until pressure and temperature grew high enough to ignite nuclear fusion. The sun was born. In the surrounding disk, dust particles stuck together, gradually building up into pebbles, boulders, and eventually planets. The entire process took about 50 million years, remarkably fast on cosmic timescales. The Sun contains 99.86% of the total mass of the solar system. All the planets, moons, asteroids, and comets combined make up barely more than 0.1%. Jupiter, the largest planet, accounts for most of that small fraction. This shows just how dominant the Sun is gravitationally. It is the anchor around which everything else orbits. The Sun is a sphere of hot plasma, held together by its own gravity and powered by nuclear fusion in its core. Every second, the Sun converts about 600 million tons of hydrogen into helium, releasing vast amounts of energy that lights up the solar system. Mercury is the smallest planet and the closest to the Sun. This little world is only slightly larger than Earth's moon. It has a surface covered with craters, blasted by billions of years of asteroid impacts. Mercury has virtually no atmosphere to protect it or to moderate temperatures, so it experiences wild extremes. During the day, temperatures can reach 430 degrees Celsius, hot enough to melt lead. At night, it plunges to minus 180 degrees Celsius. Mercury also has a very long day. It takes 59 Earth days to complete one rotation on its axis, but only 88 Earth days to orbit the Sun. Venus is the hottest planet in the solar system, even though Mercury is closer to the Sun. Venus has a thick atmosphere, 90 times denser than Earth's, made mostly of carbon dioxide with clouds of sulfuric acid. This creates a runaway greenhouse effect, trapping heat and raising surface temperatures to an average of 460 degrees Celsius. The atmospheric pressure at the surface is so intense it would crush a human instantly. Soviet Venera landers that touched down on Venus in the 1970s survived less than 2 hours before succumbing to the hellish conditions. Despite being similar in size to Earth, Venus is a world of extremes, hostile and forbidding. Earth is the only known planet to support life. Our world is a perfect balance of conditions. Liquid water covers about 70% of the surface. We have an atmosphere rich in nitrogen and oxygen that protects us from harmful solar radiation while keeping temperatures stable. A magnetic field generated by our iron core shields us from charged particles streaming from the Sun. Earth is at just the right distance from the Sun, in the so-called habitable zone, where temperatures allow water to exist as a liquid. All of these factors combine to create an oasis of life in the cold vacuum of space. As far as we know, Earth is unique in the universe, though we are searching for other worlds that might harbor life. Mars is called the red planet because of iron oxide, or rust, on its surface. This rust gives Mars its distinctive reddish hue. Mars is about half the size of Earth and much colder, with average temperatures around minus 63 degrees Celsius. Its atmosphere is thin, mostly carbon dioxide, and provides little protection from radiation or meteorites. But Mars is fascinating because it once had liquid water on its surface. Ancient riverbeds and lake basins scar the landscape, evidence of a warmer, wetter past billions of years ago. Today, ice exists at the poles and underground. NASA's rovers are exploring Mars, searching for signs that life may have existed there long ago. Jupiter is the largest planet in the solar system. This gas giant is so massive that all the other planets combined could fit inside it, with room to spare. Jupiter is more than 300 times the mass of Earth. It is made mostly of hydrogen and helium, with no solid surface. Beneath the thick clouds lies an ocean of liquid metallic hydrogen surrounding a rocky core. Jupiter's gravity is immense, and it has played a crucial role in shaping the solar system. It acts like a cosmic vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise threaten the inner planets. Jupiter has at least 95 known moons, including Ganymede, the largest moon in the solar system, even larger than the planet Mercury. The Great Red Spot on Jupiter is a storm that has raged for at least hundreds of years. This gigantic anticyclone is large enough to swallow 2 or 3 Earths. Winds in the storm exceed 400 kilometers per hour. Observations show that the Great Red Spot has been shrinking over the past few decades, though scientists are not entirely sure why. It may eventually disappear, only to be replaced by new storms. Jupiter's turbulent atmosphere is a churning sea of clouds, lightning and powerful storms, driven by the planet's rapid rotation and internal heat. Saturn is famous for its stunning rings. These rings are made of countless chunks of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings stretch out hundreds of thousands of kilometers, but are remarkably thin, sometimes only tens of meters thick. From edge on, they almost disappear from view. No one knows for certain how the rings formed, but they may be the remnants of a shattered moon or comet. Saturn itself is a gas giant, the second largest planet, with a density so low it could float in water if you could find a bathtub large enough. Saturn has at least 146 known moons, the most of any planet. Uranus rotates on its side. Most planets spin more or less upright, with their axes tilted only slightly. But Uranus is tilted 98 degrees, meaning it essentially rolls around the Sun like a ball. This strange orientation may be the result of a massive collision with an Earth-sized object early in the solar system's history. Because of this tilt, Uranus has extreme seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Uranus is an ice giant with a thick atmosphere of hydrogen, helium, and methane. The methane absorbs red light, giving the planet its distinctive blue-green color. Neptune is the most distant planet from the Sun and one of the windiest. Despite being so far from the Sun's warmth, Neptune has incredibly active weather. Winds can reach 2,000 kilometers per hour, the fastest in the solar system. Storms rage across its blue surface, driven by internal heat. Neptune, like Uranus, is an ice giant, with a composition of water, methane, and ammonia ices surrounding a rocky core. Neptune has at least 16 known moons. The largest, Triton, is geologically active with geysers of nitrogen erupting from its surface. Triton orbits Neptune backward, suggesting it was captured from the Kuiper Belt. Pluto was reclassified as a dwarf planet in 2006. For 76 years, Pluto was considered the ninth planet. But as astronomers discovered more objects in the outer solar system, some nearly as large as Pluto, the International Astronomical Union redefined what it means to be a planet. According to the new definition, a planet must clear its orbit of other debris, and Pluto has not done so. It shares the Kuiper Belt with thousands of other icy bodies. Despite its demotion, Pluto remains fascinating. NASA's New Horizons spacecraft flew past it in 2015, revealing a complex world with mountains of water ice, plains of frozen nitrogen, and even signs of geological activity. The asteroid belt lies between Mars and Jupiter. This region contains millions of rocky bodies left over from the solar system's formation. The total mass of all asteroids combined is less than that of Earth's moon. The asteroids are spread out over a vast distance, so despite what movies show, navigating through the belt is not particularly dangerous. The largest object in the asteroid belt is Ceres, a dwarf planet about 950 kilometers across. Some asteroids are solid rock, while others are loose piles of rubble barely held together by gravity. Occasionally, asteroid collisions send fragments toward the inner solar system, where they can become meteorites that fall to Earth. The Kuiper Belt is a region beyond Neptune filled with icy bodies. This is the realm of comets, dwarf planets like Pluto, and countless smaller objects. The Kuiper Belt is like the asteroid belt, but much larger and more distant. Some Kuiper Belt objects are nearly as large as Pluto. These frozen worlds are remnants from the solar system's formation, icy leftovers that never coalesced into planets. Occasionally, gravitational interactions send a Kuiper Belt object spiraling inward, where it becomes a comet, growing a glowing tail as it approaches the Sun and its ice begins to vaporize. The Oort cloud is a vast spherical shell of icy objects surrounding the solar system. This cloud is thought to extend halfway to the nearest star, up to 100,000 astronomical units from the Sun. It has never been directly observed, but its existence is inferred from the orbits of long-period comets that take thousands or even millions of years to complete a single orbit. The Oort cloud is the edge of the Sun's gravitational influence, the boundary of the solar system. Objects there are so distant and faint that we may never see them directly, but they remain bound to the Sun, adrift in the cold, dark space between stars. Comets are dirty snowballs from the outer solar system. When a comet's orbit brings it close to the Sun, solar heat vaporizes its ices, creating a glowing coma and often a spectacular tail stretching millions of kilometers. The tail always points away from the Sun, pushed by the solar wind. Comets have been observed for millennia, often sparking fear and wonder. Ancient cultures saw them as omens. Today, we understand them as pristine samples of the early solar system, containing material unchanged since the planets formed. Studying comets helps us understand the conditions that existed 4.6 billion years ago. Earth's moon is the fifth largest moon in the solar system. It formed about 4.5 billion years ago, shortly after Earth itself. The leading theory suggests that a Mars-sized object collided with the young Earth, and the debris from that impact coalesced into the Moon. The Moon's gravity stabilizes Earth's rotation, preventing extreme wobbles that would cause chaotic climate changes. It also creates the tides, the rhythmic rising and falling of ocean waters. The Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. In the distant past, it was much closer, and days were shorter because Earth rotated faster. Billions of years from now, the Moon will be much farther away, and Earth's rotation will have slowed significantly. We always see the same side of the Moon. The Moon is tidally locked to Earth, meaning it rotates once on its axis in exactly the same time it takes to orbit Earth. This synchronization ensures that one hemisphere always faces us, while the far side, often incorrectly called the dark side, remains hidden from view. The far side was a complete mystery until spacecraft flew around the Moon and photographed it in 1959. It looks quite different from the near side, with more craters and far fewer of the large dark plains called Maria. Europa, a moon of Jupiter, may have a subsurface ocean. Beneath its icy crust lies a global ocean of liquid water, kept warm by tidal heating as Jupiter's gravity flexes and squeezes the Moon. Europa's ocean may contain twice as much water as all of Earth's oceans combined. Where there is liquid water, there is the possibility of life. Europa is one of the most promising places in the solar system to search for extraterrestrial life. NASA is planning a mission called Europa Clipper, launched in October 2024, to study this intriguing moon in detail, looking for signs of activity and assessing its potential habitability. Enceladus, a moon of Saturn, shoots geysers of water into space. The Cassini spacecraft discovered plumes of water vapor erupting from fractures near Enceladus' south pole. These geysers indicate that, like Europa, Enceladus has a subsurface ocean beneath its icy shell. The water in the plumes contains organic molecules and salts, suggesting that the ocean may have conditions suitable for life. Enceladus is small, only about 500 kilometers across, but it is one of the brightest objects in the solar system because its surface is covered with fresh, reflective ice. Studying Enceladus could reveal whether life exists beyond Earth. Titan, Saturn's largest moon, is the only moon with a thick atmosphere. This atmosphere is denser than Earth's and is mostly nitrogen, with traces of methane. Titan's surface is hidden beneath thick orange haze, but radar imaging has revealed a strange landscape of lakes and rivers, not of water, but of liquid methane and ethane. Titan is the only other body in the solar system besides Earth with stable liquid on its surface. It has weather with methane rain falling from clouds and carving channels into the icy surface. The temperature is a frigid -179 degrees Celsius, but Titan's complex chemistry makes it another target in the search for life, or at least prebiotic molecules. Io, another moon of Jupiter, is the most volcanically active body in the solar system. Tidal forces from Jupiter constantly squeeze and stretch Io, generating enormous internal heat. This heat drives hundreds of active volcanoes that spew sulfur and sulfur dioxide, painting the surface in vivid yellows, oranges, and reds. Some volcanic plumes shoot material hundreds of kilometers into space. Io has no impact craters because volcanic activity constantly resurfaces the moon, erasing any scars. It is a world of fire and sulfur, a hellish landscape in constant upheaval. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It is the only moon known to have its own magnetic field, generated by a liquid iron core. Ganymede has a mix of ancient, heavily cratered terrain and younger, grooved regions that suggest past geological activity. Like Europa and Enceladus, Ganymede is thought to have a subsurface ocean, buried deep beneath multiple layers of ice. If confirmed, Ganymede would join the growing list of ocean worlds in our solar system, places where life might possibly exist. Triton, Neptune's largest moon, orbits backward. Most large moons orbit in the same direction as their planet's rotation, but Triton orbits in the opposite direction. This suggests Triton was not formed along with Neptune, but was captured from the Kuiper Belt. Triton is geologically active, with geysers of nitrogen gas erupting from its surface. It is one of the coldest places in the solar system, with surface temperatures around -235 degrees Celsius. Triton's retrograde orbit is gradually bringing it closer to Neptune. In a few billion years, it will cross the Roche limit and be torn apart by tidal forces, forming a spectacular ring system around Neptune. Moons come in a wide variety of sizes and compositions. Some are tiny, irregular chunks of rock and ice captured by a planet's gravity. Others are large, spherical worlds with complex geology. Some moons are geologically dead, their surfaces frozen in time, covered with ancient craters. Others are active, with volcanoes, geysers, or shifting ice. Studying moons teaches us about planetary formation and evolution. They are windows into processes that shaped the solar system billions of years ago and continue today. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse at the end of their lives. If the core is more than about 3 times the mass of the Sun, nothing can stop the collapse. The core shrinks to an infinitely small point called a singularity, surrounded by an event horizon, the boundary beyond which escape is impossible. Black holes are invisible by nature, but we can detect them by their effects on nearby matter. Gas and stars swirl around black holes, heated to millions of degrees, emitting intense X-rays that we can observe. Supermassive black holes sit at the centers of most galaxies. These monsters can contain millions or even billions of times the mass of the Sun. No one is entirely sure how they formed, but they seem to have existed very early in the universe's history. The Milky Way's supermassive black hole, Sagittarius A star, is relatively quiet now, but it occasionally flares as gas and dust fall into it. In May 2022, astronomers released the first direct image of Sagittarius A star, showing the glowing ring of hot material swirling around the event horizon. Time slows down near a black hole. This is not science fiction. It is a consequence of Einstein's theory of general relativity. Gravity warps space and time itself. The closer you get to a black hole, the slower time passes relative to someone far away. If you could watch a clock falling into a black hole, you would see it tick slower and slower, eventually appearing to freeze at the event horizon. For the falling clock, time continues normally, but for an outside observer, it seems to take forever to cross that boundary. Near black holes, space and time behave in ways that defy everyday intuition. If you fell into a black hole, you would experience spaghettification. This is the scientific term for what happens when tidal forces stretch an object. Near a black hole, the gravitational pull on your feet, if you fell feet first, would be enormously stronger than the pull on your head. This difference would stretch you like a noodle, pulling you thinner and longer until you were torn apart at the atomic level. For smaller black holes, this would happen before you even crossed the event horizon. For supermassive black holes, the tidal forces are weaker, and you might survive crossing the horizon before being destroyed deeper inside. Black holes evaporate over time through Hawking radiation. In 1974, physicist Stephen Hawking predicted that black holes are not entirely black. Quantum effects near the event horizon allow them to emit a faint glow of radiation. Over immensely long timescales, far longer than the current age of the universe, black holes will slowly lose mass and eventually evaporate completely. For stellar mass black holes, this process would take 10 to the power of 67 years. For supermassive black holes, it would take even longer. But in the unimaginably distant future, when all stars have died and galaxies have faded, Hawking radiation will be the universe's last whisper of energy before it fades into eternal darkness. The first image of a black hole was captured in 2019. The Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the supermassive black hole at the center of the galaxy Messier 87. The image shows a bright ring of light, the glowing accretion disk surrounding a dark central region, the shadow of the black hole's event horizon. This was a historic moment in astronomy, the first direct visual evidence of a black hole. It confirmed decades of theoretical predictions and opened new ways to study these mysterious objects. Neutron stars can spin hundreds of times per second. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams. If one of those beams points toward Earth, we see a pulse of radio waves with incredibly precise timing. Some pulsars rotate faster than a kitchen blender, completing hundreds of rotations every second. These millisecond pulsars are so regular, they rival atomic clocks in their precision. Astronomers use them as cosmic timekeepers and to test fundamental physics, such as gravitational wave detection. Magnetars have the strongest magnetic fields in the universe. These rare neutron stars have magnetic fields trillions of times stronger than Earth's. The magnetic field is so intense it distorts the shape of atoms on the surface. Occasionally, magnetars undergo starquakes, releasing bursts of X-rays and gamma rays so powerful they can affect Earth's upper atmosphere from thousands of light years away. Magnetars are among the most extreme objects known, showcasing what happens when matter and energy are pushed to their limits. Gravitational waves are ripples in space-time. When massive objects like black holes or neutron stars orbit each other and eventually merge, they create waves that spread outward at the speed of light, stretching and compressing space itself. These waves were predicted by Einstein's general relativity in 1915, but were not directly detected until September 2015. when the LIGO observatories measured gravitational waves from two merging black holes. This discovery opened an entirely new way to observe the universe, one that does not rely on light. Gravitational wave astronomy is still in its infancy, but it has already transformed our understanding of cosmic collisions. Wormholes are theoretical shortcuts through space and time. These hypothetical tunnels connecting distant parts of the universe are allowed by the equations of general relativity, though we have never found one and do not know if they can actually exist. If they could, wormholes might allow faster-than-light travel by bypassing normal space. However, keeping a wormhole open would require exotic matter with negative energy, something we have never observed. For now, wormholes remain in the realm of speculation and science fiction, tantalizing possibilities that hint at the strange flexibility of space-time. Time dilation affects astronauts on the International Space Station. Although the effect is tiny, astronauts orbiting Earth experience time slightly differently than people on the ground. Two factors are at play. First, the astronauts are moving faster, which causes time to slow down slightly according to special relativity. Second, they are farther from Earth's mass, where gravity is weaker, which causes time to speed up slightly according to general relativity. The second effect is larger, so astronauts age very slightly faster than people on Earth. Over months in space, an astronaut might age a few milliseconds more than someone on the ground. These tiny differences have been measured and confirm Einstein's predictions. Exoplanets are planets that orbit stars other than our Sun. Before 1992, we had never confirmed a planet outside our solar system. Today, we have confirmed more than 5,600 exoplanets, with thousands more candidates awaiting verification. These planets come in a stunning variety. Some are gas giants larger than Jupiter, orbiting so close to their stars they complete an orbit in days. Others are rocky worlds similar to Earth. Some orbit in the habitable zones of their stars, where temperatures might allow liquid water. Discovering exoplanets has revolutionized our understanding of planetary systems and raised the exciting possibility that Earth-like worlds may be common in the universe. The first exoplanet around a Sun-like star was discovered in 1995. Astronomers Michel Mayor and Didier Queloz detected a planet orbiting the star 51 Pegasi. This discovery earned them the Nobel Prize in Physics in 2019. The planet, a gas giant about half the mass of Jupiter, orbits extremely close to its star, completing an orbit in just 4 days. This was unexpected. At the time, most scientists assumed planetary systems would resemble our own, with small rocky planets close in and gas giants farther out. The discovery of 51 Pegasi b, a so-called hot Jupiter, challenged those assumptions and opened a new field of study. Some exoplanets orbit two stars. These circumbinary planets, sometimes called Tatooine planets after the famous Star Wars world, experience sunsets with two suns. Several such planets have been discovered, and their existence was a surprise to astronomers. Forming a planet in a binary star system is difficult because the gravitational pulls from two stars can disrupt the disk of material from which planets form. Yet nature found a way. These planets demonstrate that planetary systems can exist in a wider range of environments than we once thought. Rogue planets drift through space untethered to any star. These lonely worlds were either ejected from their home systems or formed in isolation. They wander through the galaxy in darkness, receiving no warmth from a nearby sun. Some rogue planets might retain internal heat from their formation or from radioactive decay, keeping their cores warm even as their surfaces freeze. It is possible that some rogue planets have subsurface oceans kept liquid by this internal heat. If so, they might harbor life in the cold darkness of interstellar space, completely cut off from the light of any star. The nearest exoplanet is Proxima Centauri b. This rocky world orbits Proxima Centauri, the closest star to our solar system, just 4.2 light-years away. Discovered in 2016, Proxima b is only slightly more massive than Earth and orbits in its star's habitable zone. However, Proxima Centauri is a red dwarf, a type of star known for violent flares that could strip away a planet's atmosphere. Whether Proxima b could support life is unclear, but its proximity makes it a prime target for future study. If humanity ever sends a probe to another star system, Proxima Centauri would likely be the first destination. Some exoplanets are made of diamond. Carbon-rich planets, if they exist, could have interiors and surfaces dominated by carbon compounds rather than the silicates and iron common on Earth. Under immense pressure, carbon forms diamond. These worlds might glitter beneath thick atmospheres, although no one has yet confirmed their existence. The idea of diamond planets remains speculative, but serves as a reminder that planets can be far more varied in composition than we ever imagined. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Many discovered exoplanets fall into this category, even though our solar system has no examples. Some super-Earths orbit in habitable zones, raising the possibility they could support life. Their larger size means stronger gravity, which might help them retain atmospheres. However, we do not yet know what conditions are like on these worlds. Some might be ocean planets entirely covered by deep water. Others might be barren with crushing atmospheres. Super-Earths are diverse, and studying them will teach us much about planetary formation and evolution. Hot Jupiters are gas giants that orbit very close to their stars. These massive planets, similar in size to Jupiter, circle their stars in just a few days, their atmospheres heated to thousands of degrees. Hot Jupiters were among the first exoplanets discovered because their large size and close orbits make them easy to detect. Their existence was surprising. In our solar system, gas giants are far from the Sun. Hot Jupiters likely formed farther out and migrated inward over time, possibly displacing or destroying smaller planets in their path. Their discovery reshaped our theories of how planetary systems form and evolve. The Kepler Space Telescope discovered thousands of exoplanets. Launched in 2009, Kepler stared at a single patch of sky, monitoring over 150,000 stars for signs of planets. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. By detecting these transits, Kepler identified thousands of planets. Its mission transformed our understanding of how common planets are. We now know that nearly every star has at least one planet, and rocky planets in habitable zones are not rare. Kepler's data will keep astronomers busy for decades, revealing patterns and oddities in the planetary census. TRAPPIST-1 is a star with 7 Earth-sized planets. Discovered in 2017, this remarkable system lies about 40 light-years away. 3 of the planets orbit in the habitable zone, where liquid water could exist. The planets are packed tightly together, closer to their star than Mercury is to our Sun. But TRAPPIST-1 is a small, cool red dwarf, so the planets receive less heat. If life exists on any of these worlds, we might one day detect it by studying their atmospheres for biosignatures like oxygen or methane. TRAPPIST-1 is one of the most exciting planetary systems for astrobiology. Dark energy is causing the universe to expand faster over time. We do not know what dark energy is, but we know what it does. It acts as a kind of anti-gravity, pushing space apart. The more space there is, the more dark energy, so the expansion accelerates. Dark energy makes up about 68% of the universe's total energy, yet we have no idea what it is. Solving this mystery is one of the greatest challenges in physics. Dark energy will determine the ultimate fate of the universe, whether it expands forever, tears itself apart, or collapses back in on itself. Dark matter outweighs visible matter by a factor of 5 to 1. Despite being invisible, dark matter's gravitational influence is everywhere. It forms vast halos around galaxies, shapes the cosmic web, and affects how light bends as it passes through space. Astronomers have tried for decades to detect dark matter particles directly, but so far without success. We do not know if it is made of unknown subatomic particles, primordial black holes, or something else entirely. Dark matter is one of the universe's deepest mysteries, a hidden framework that holds everything together. Cosmic rays are high-energy particles racing through space. Most are protons, accelerated to nearly the speed of light by supernova explosions, pulsars, and other violent cosmic events. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles. Billions of cosmic rays pass through your body every day, though they are mostly harmless. Studying cosmic rays helps us understand the most energetic processes in the universe. Some cosmic rays carry so much energy that scientists still do not know what could accelerate them to such speeds. The cosmic web is the largest structure in the universe. Galaxies are not scattered randomly through space. They cluster along vast filaments, forming a web-like pattern on the largest scales. These filaments are hundreds of millions of light-years long, separated by enormous voids containing very few galaxies. The cosmic web formed from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Mapping this structure helps us understand how matter clumps together and how the universe evolved from smooth beginnings to the rich, complex cosmos we see today. Voids are enormous empty regions of space. These cosmic deserts contain very few galaxies, sometimes spanning hundreds of millions of light-years. They are not truly empty. Gas and dark matter exist in voids, but they are far emptier than the filaments and clusters surrounding them. Voids make up most of the universe's volume. Understanding why some regions remain underdense while others become rich in galaxies is an active area of research. Voids are shaped by the same gravitational forces that create clusters, just working in reverse, pushing matter outward rather than pulling it inward. Redshift tells us how fast distant galaxies are moving away. When a galaxy moves away from us, the light it emits is stretched to longer, redder wavelengths. This is called redshift. The farther away a galaxy is, the faster it recedes, and the greater its redshift. By measuring redshift, astronomers can determine a galaxy's distance and the expansion rate of the universe. The most distant galaxies have redshifts so large that their ultraviolet light is stretched into the infrared. These galaxies are seen as they were billions of years ago, offering a glimpse of the universe's infancy. The universe has no center. It might seem like the Big Bang happened at a specific point, but actually, it happened everywhere at once. Space itself expanded, carrying matter with it. There is no central location from which the universe is expanding. Every point in space sees other points moving away, just as we see distant galaxies receding in all directions. This is one of the hardest concepts to grasp, but it is fundamental to modern cosmology. The universe is not expanding into anything. Space itself is growing. Time began with the Big Bang. Before the Big Bang, there was no time, no space, no matter, nothing as we understand it. The concept of before the Big Bang may not even make sense because time itself came into existence at that moment. This idea stretches the limits of human comprehension. We are used to thinking of cause and effect, of events happening in sequence, but at the origin of the universe, such concepts break down. Cosmologists continue to explore theories of what might have existed before the Big Bang, if anything, but these ideas remain speculative and untested. The universe might be infinite. We can only see a finite portion, the observable universe, limited by the speed of light and the age of the universe. But beyond that horizon, space may continue forever. If the universe is infinite, it has always been infinite, even at the moment of the Big Bang. An infinite universe would contain an infinite number of galaxies, stars, and planets. Somewhere out there, there might be exact copies of you, living identical or slightly different lives. This is a consequence of infinity combined with probability. Though mind-bending, it is a legitimate possibility in cosmology. The future of the universe depends on its density. If the universe contains enough matter, gravity will eventually halt and reverse the expansion, leading to a big crunch. If there is not enough matter, the universe will expand forever, growing colder and darker until all stars burn out, leaving only black holes and dead remnants, a scenario called the Big Freeze. Current observations suggest the Big Freeze is more likely, especially given the influence of dark energy. In the far future, galaxies will drift apart, stars will die, and the universe will fade into a cold, dark, nearly empty expanse. But that end lies trillions of years away. The speed of light is the ultimate speed limit. Nothing with mass can reach or exceed the speed of light, which is approximately 300,000 kilometers per second in a vacuum. This limit is built into the fabric of space-time itself. As an object accelerates closer to light speed, it requires exponentially more energy to go faster. At light speed, time stops and distances shrink to zero from the perspective of the object. Light itself always travels at this speed, never faster, never slower, regardless of the motion of the source or observer. This constancy is the foundation of Einstein's special relativity. Photons from distant stars have traveled for millions or billions of years to reach your eyes. When you look at the night sky, you are literally seeing the past. The light from Sirius, the brightest star in the night sky, left that star 8.6 years ago. Light from the Andromeda Galaxy began its journey 2.5 million years ago, when early humans were just beginning to use tools. Some of the faintest galaxies detected by the James Webb Space Telescope are seen as they appeared over 13 billion years ago, when the universe was only a few 100 million years old. Astronomy is time travel, not into the future, but deep into the past. The Hubble constant measures the rate of the universe's expansion. Named after Edwin Hubble, who discovered the expansion in 1929, the Hubble constant tells us how fast galaxies are receding based on their distance. However, measurements of the Hubble constant from different methods give slightly different results, a problem called the Hubble tension. This discrepancy suggests we may be missing something fundamental about the universe's composition or the way it expands. Resolving this tension is one of the most important goals in cosmology today. The multiverse is a speculative idea that our universe might be one of many. Some theories in physics, particularly those involving inflation and string theory, suggest that other universes could exist beyond our own, each with potentially different physical laws and constants. These universes would be completely separate from ours, unreachable and undetectable. The multiverse remains highly controversial. Some scientists embrace it as a natural consequence of existing theories. Others dismiss it as untestable and therefore not science. The debate continues, but for now, the multiverse remains an intriguing possibility rather than established fact. Cosmic inflation was a period of incredibly rapid expansion just after the Big Bang. In the first fraction of a second, the universe expanded exponentially, growing from smaller than an atom to macroscopic size in an instant. This theory, proposed by Alan Guth and others in the early 1980s, solves several problems with the standard Big Bang model. It explains why the universe is so uniform on large scales and predicts the tiny fluctuations that became galaxies. Evidence for inflation comes from detailed measurements of the cosmic microwave background. Though inflation is widely accepted, some details remain uncertain, and physicists continue refining the theory. Antimatter is matter's mirror image. For every particle, there is an antiparticle with the same mass but opposite charge. When matter and antimatter meet, they annihilate in a burst of energy. The early universe contained equal amounts of matter and antimatter, but something caused a slight imbalance, leaving a universe dominated by matter. If matter and antimatter had been perfectly balanced, they would have annihilated completely, and the universe would contain only energy. No atoms, no stars, no us. Why this asymmetry exists is one of physics' greatest unsolved problems. We are made of stardust. Every element heavier than hydrogen and helium was forged in the cores of stars or in supernova explosions. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all came from stars that died billions of years ago. Those elements were scattered into space, mixed with clouds of gas and dust, and eventually incorporated into the solar system when it formed. You are not just in the universe, you are of the universe, assembled from the ashes of ancient stars. This connection links every living thing on Earth to the cosmos. The Fermi paradox asks, where is everybody? If the universe is vast and ancient, filled with billions of galaxies and trillions of planets, why have we not detected any signs of intelligent alien life? The physicist Enrico Fermi famously posed this question in 1950. Possible answers include: life is extremely rare. Intelligent civilizations destroy themselves before they can spread. Interstellar travel is too difficult. We are not looking in the right ways. Or perhaps aliens are out there but deliberately avoiding contact. The Fermi paradox remains unresolved, a reminder that despite our knowledge, we still do not know if we are alone in the universe. The Drake equation estimates the number of communicative civilizations in the galaxy. Formulated by astronomer Frank Drake in 1961, the equation multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, and the likelihood of life arising and developing intelligence. The problem is, we do not know most of these values with certainty. Depending on the assumptions, the Drake equation can predict anything from one civilization, us, to thousands or millions. It is not a precise tool, but rather a framework for thinking about the search for extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, listens for signals from alien civilizations. For decades, astronomers have pointed radio telescopes toward promising star systems, hoping to detect deliberate transmissions or accidental leakage from advanced technologies. So far, SETI has found nothing conclusive. The most famous candidate signal, the WOW signal detected in 1977, lasted 72 seconds and has never been explained or repeated. SETI continues expanding to new wavelengths and using more sophisticated analysis. The silence so far does not mean aliens do not exist. It may simply mean the universe is vast, and signals are rare and fleeting. Techno-signatures are signs of advanced technology. Beyond radio signals, scientists are now considering other ways to detect alien civilizations. These include unusual chemical compositions in exoplanet atmospheres, artificial structures like Dyson spheres that surround stars to harvest energy, or even laser pulses used for communication or propulsion. As our instruments improve, we may be able to detect these techno-signatures if they exist. The search is broadening, recognizing that alien technology might not resemble our own and could be centuries or millennia ahead of us. And so, we come gently to the end of our journey through 100 facts about space. From the birth of the universe in a blaze of energy to the slow dance of galaxies across billions of years. From the fiery hearts of stars forging the elements of life itself to the cold, dark regions where planets drift alone. From the mysteries of dark matter and dark energy, which shape everything yet remain invisible, to the question that echoes in every human heart. Are we alone? You have traveled far tonight, through time and space, across distances your mind can barely hold. You have glimpsed the ancient past in the light of distant stars, and you have looked toward a future stretching trillions of years into the darkness. The universe is vast, beautiful, and strange. It is full of wonders we have only begun to understand, and mysteries that may never be fully solved. And yet, we are part of it. The atoms in your body, the thoughts in your mind, the breath in your lungs, all of it is woven from the same cosmic fabric that makes stars and galaxies. Tonight, as you rest, the universe continues its slow unfolding. Stars are born and die. Black holes spiral together, sending ripples through space-time. Galaxies drift through the dark. And you, a small collection of stardust, conscious and aware, float gently through it all. You are not separate from the cosmos. You are the universe experiencing itself, a brief spark of awareness in an ocean of space and time. If you happen to still be awake, you can watch the next chapter now. But if sleep has found you, then rest well. Dream softly of stars and galaxies, of planets and moons, of the infinite mysteries still waiting to be discovered. The universe is patient. It will be there when you wake. Good night.